Welcome to example number 9. We have a inclined plane system with two blocks, both having the same mass, and there's friction along this inclined plane. And the angle here is 25 degrees. We're asked to determine the acceleration of the block, and hence the other mass that's hanging, the same acceleration of the system. Now there is one little issue with this problem that I did realize after looking at this problem. We should have been told what direction the system is moving, because that will determine what direction the kinetic friction is moving. So let's make an assumption right off in the beginning, and we're going to assume the hanging block is initially moving downwards. Otherwise, you would get two different answers, because if the system was initially in the opposite direction, where the hanging block was moving upwards, then the friction would be in the opposite direction that it was moving on this block and be going up the inclined plane. And we would get two possible answers. So we'll look for one answer and say that the system is moving along in this direction initially. That's the initial velocity of the system. This is going down. Okay, so solving this problem, the first thing we're going to do is to draw a free body diagram for both the block on the inclined plane and the hanging block. So let's go ahead and do that. So for the mass on the inclined plane, we have a force of gravity, mg. We have a normal force. We have a tension. And then we have friction moving in the opposite direction that it's sliding, so going down the ramp. For the rock that's hanging here, we have the tension, and then we have the weight, mg, going down as well. And both of them have the same mass. Next, I'll assume the direction of the acceleration. So let's assume that this mass, this rock, is moving downwards and accelerating in the same direction. And same thing here. This is going up the inclined plane. Now, we can solve this individually, both masses, and find the acceleration by working with two equations and two unknowns. But what I think might be interesting to follow is use a system of masses. So let's define an interesting system here. Okay, so what I've done is I've kind of thought of taking this rock and swinging it up here, and we're going to look along an axis like this, and I've just drawn it horizontally. So imagine that now the tension is here on the block on the inclined plane. The rock tension is going back here, Ft. We have an mg force pulling this down. We're just going to draw it right. We have a mg in this case going down here at an angle. We have the normal force drawn, and then we have the friction going backwards, if that helps you visualize it. Or you could think of an axis going all along here and then coming down like through here. So we're going to consider a system that is the rock and the block together. So this along this dotted line here is our system, so both of them together here. And I've drawn an axis in here, and this is our axis, we'll say just as the x-axis. And over here, this angle right in here is 25 degrees. That's the same angle that is over here. That is 25 degrees. And how do we get that? This is 25 in here, between the incline and the plane, or the ground and the plane. And then this is 90, and this must be 90 minus the angle, which is 65 degrees. And if that's 65 degrees in here, that is 65 as well, because this is the same parallel axis as it would be here, or this one here and here is the same angle right in there. And so therefore this angle right in here is the same as 25 degrees. So it would be 90 minus 65, which gives you 25. Okay, so now let's apply Newton's second law. Sum of the forces of the system we're going to use along the x-axis equals ma. But this is the mass of the system. So this really should be actually 2m, because there's an m here and there's an m here, so there's a total mass of 2m. And the forces that are causing it to accelerate in that direction here is mg, the hanging rock, The tensions here would both be considered internal forces, so they would cancel out. We have the force of friction, Ff, and then we have the x component of this mg, which is mg sine theta, and that is equal to 2m times a. We can rewrite the friction now as mu times the normal force, Fn, minus mg sine theta equals 2ma. By the way, this is a kinetic coefficient of friction. And now the last thing we need to do is find that normal force. If we sum the forces in the y-axis for this particular body right here, we would find that the normal force minus the y component of the weight, which is this y component in here, which is mg cosine theta, will balance out to give you 0. So the normal force is equal to mg times cosine theta. So now we're going to plug that expression into here. We have mg minus mu k times mg cosine theta minus mg sine theta equals 2 times m times a. And you can see that the m's will all cancel out, and we'll get the following expression. We can see that there's a g in each term, so we'll put out a g divided by 2, and then we'll have 1 minus mu cosine theta minus sine theta. So all we need to do now is plug into this expression 9.8 meters per second squared divided by 2, and then 1 minus coefficient of kinetic friction, which is 0.15, times the cosine of the angle, which is 25 degrees, minus the sine of 25 degrees, and go ahead and plug that into your calculator. And you should get an answer of 2.16 meters per second squared. Now, alternatively, had we assumed the velocity was going initially down the ramp, and we would find that this weight would be enough to slow the system down and decelerate and still cause an acceleration upwards, you would get a very similar expression, except now friction would be going up the ramp, helping it in the direction that it's accelerating. So you would have mg now plus the force of friction minus mg sine theta. And so the only term that would change is there would be a plus here and a plus here, and I think your final answer would be, in the end, 3.5 meters per second squared. So I suppose we could get 3.5 meters per second squared had we assumed an initial velocity in the opposite direction. Okay, and that's it for example number 9.